Okay, let's continue the discussion. So we already introduced this so-called postulate 1, the field axioms. Let me explain a little bit about the name, what field means. So in the algebra, especially in the abstract algebra, we have the following list of the concepts. First, when you have a set, we can define an operation. Operation is an operation. This operation requires two inputs, so sometimes it's also called the binary operation. And this operation gave a value also in this set x. So we may write this way. This operation is from x cross x to x. This is a binary. So it means with this operation, the result is still in x. So the operation, the x is closed under the operation. So it's closed under the operation. Okay, so that's what we mean closed. The image is still in x. And for example, you have a and b, then we write it as a dot. A dot b is in x for all a, b in x. Okay, so we have a binary operation over x with the image in x. X is closed. And if a dot b is equal to b dot a, we say this operation commutative. We say this operation is commutative. And sometimes when it is commutative, we prefer to use plus instead of a dot. So we may use a plus b instead of a dot b, but this is still an operation. Here, this plus just is an abstract operation. It does not always mean the addition of numbers. So it's just a operation. Okay, so for example, if we have all natural numbers, all natural numbers, we denoted by n natural numbers. So they are 1, 2, 3, 4. And together with addition, the regular number addition, with addition. So this addition is a binary operation over the natural numbers. Okay? And for this kind of binary operation, if there is a special one, a special element, let's call it E, in X, such that E plus A is A plus E. If this happens, then E is called the identity. E is called the identity or the neutral element Okay. This identity, see here, this place we say a special element. Maybe there's another one, but here we call the identity. Actually, if you have more than one, they should be equal, because if E1 satisfy that E1, okay, if E1, E2 are both identities. Then first, let's see. We consider A as a E1. So E1 is equal to E1 plus E2 because E2 is identity. And this time we consider A as E2. E1 is identity, so it's equal to E2. So we do have E1 equal to E2. So the identity is definitely unique. So this part, you consider A is equal to E1. And this part, you consider A is equal to E2. You apply this property. So anyway, I go through this not very slow because you will definitely study this in the abstract algebra, modern algebra. Okay? So identity is unique. With the identity, we can discuss the inverse. First of all, not every set with a binary operation has identity. For example, the set of natural numbers has no identity because it does not include 0. With 0, it has identity. Without 0, it has no identity. Okay? Okay, after you have identity, if for every A in X, there is a unique element B in X such that A plus B is equal to B plus A is equal to the identity, then B is called the inverse of A, denoted B is equal to negative A. Okay? So this is the inverse. Okay. So that's the definition of inverse. The set of all integers has an identity, has the identity, and every element has its inverse. Then and the binary operation is a commutative. The binary operation is commutative. Then it is called an abelian group. Abelian group. Okay? So what is an abelian group? You have a set, you have a binary operation, it is commutative, it has identity, every element has inverse, then it's a abelian group. Z is a abelian group. And N is not a abelian group. It does not have a identity. Also, every element has no inverse. It is commutative. That is sometimes we call it semigroup. Okay, semigroup. Okay, so that's a group. Remember, on this level we have a group. Then for the group, for an abelian group, let's call it a G. It already has an operation. If it has a second operation, assume G has a second commutative commutative or not, second binary operation. Let's don't require commutative. If it has second binary operation, because the first binary operation we denoted by the plus, second we use the dot, the multiplication. Okay, the second binary operation and satisfying a dot b plus c is equal to a dot b plus a dot c, and b plus c dot a is equal to b dot a plus c dot a. We don't require the commutativity so far. If it has commutative, this second condition is useless. If it does not have commutativity, both conditions are required. Okay, if this is satisfied, G is called a ring. G is called a ring. If it is commutative, it's called a commutative ring. Okay, so if the second multiplication operation is commutative, it's called a commutative ring. Without this condition, it's just called a ring. Okay, so you can see that the integers has addition, also has a multiplication. So Z is a commutative ring. Z is a commutative ring. All right, and for the second binary operation, so you see here we only require the binary operation. We didn't require it has a identity, it has a inverse stuff. So if the second operation has the identity, then G is called a unit ring. We say G has a unit, this identity. The identity for the second operation is called the unit. The unit ring. Okay? If for the second operation, we consider second operation, every non-zero, this zero is the identity from the first operation. This zero is identity of the first operation. Every non-zero element has its inverse. Okay? If for the second operation you also have identity and the inverse, then G is called a division ring. Why it's called a division ring? It's because, you see, remember the second operation, we recall it as a dot. So for A in G, there is B in G such that A times B is equal to 1. This 1 is a unit for the second binary operation. 0 is a unit for the first operation. 0 is a unit for the commutative. Okay, this is always commutative. This one, I don't know if it's commutative or not. It may or may not be commutative. Okay, so this is inverse. For this inverse, we denote B as either A to -1 or 1 over A. Okay, that's just a notation. It is just a notation. So from this notation, it looks like we do the division. So you see that C times B, it looks like C times 1 over A if you have this relation. So it's like C over A. It's like division. So that's why if the second binary operation for the second binary operation, it has inverse, identity and inverse for each element, then it's called a division ring. If the second operation, if the second operation is commutative, if we emphasize this condition, so you see here, if the second operation is commutative, this division ring is called a field. It's called a field, right? You see here, Z is a commutative ring, but Z is not a division ring because inside the Z you cannot always do division, right? If you want to do the division, you will get the rational numbers. The set of all rational number quotient, this Q comes from the quotient. The set of all rational numbers, it is a field. You can do the division. You see, whenever you do division, you will exclude 0 as a denominator because 0 has no inverse. We don't require 0 to have inverse. All right, so Q, the set of all rational numbers, is a field. R, the set of all real numbers, is also a field. They're different. Q is smaller, R is bigger. And this is the reason we call this postulate the field axiom. So technically, the field axiom, you will see it just verify all the requirement for two operations. It has addition, it has subtraction. Subtraction is actually the inverse of addition. It has a multiplication, that's the second operation. It has a division. The division comes from the inverse of the multiplication. It has the distribution law. This one is a distribution law. Those two operations should be compatible. Okay, so all 8 conditions are just the verification of the definition of field. Again, a field, what is a field? Field means you can do addition, subtraction, multiplication, and division. When you do division, you cannot divide by 0. So whenever you can do those 4 operations, it is a field. If you can only do 3 operations, addition, subtraction, multiplication, it is a ring. If you can do just 2, it's a group. If you can just do 1, it's a semigroup. Am I clear? So with plus semigroup, plus minus group, plus minus product ring, plus minus product division field. Okay. Okay. So that's a very brief discussion about the abstract algebra. It's just a classification or extension about the operations for the same set. Okay, so from this requirement, all 8 conditions, we can actually get some properties. The property will be that -1 times -1 is equal to +1. Okay, so you can try to get y -1 times -1 is equal to +1. And also 0 times a is always equal to 0. Remember, those stuffs are not directly given, even though we know it is clearly. But if we just start from the postulate, if we only start from the postulate, all those statements are not straightforward. You have to do some computation. For example, how do we do it? For example, let's do this one. This one is simpler. So 0, we know 1 plus -1 is equal to 0. Right? 1 plus negative 1 is equal to 0. And then what we get? We get 1 plus negative 1 times a is equal to 1 times a is a. Negative 1 times a, I don't know. It's just this. Okay? We don't need this. This one is a condition. Is a conclusion. We don't need this. We don't need this. Let's continue. Sorry. 0 times a is equal to 0. Why? So 0 is the identity of the addition. So 0 is equal to 0 plus 0. 0 is equal to 0 plus 0. And then you have 0 times a, it is equal to 0 plus 0 times a. And 0 plus 0 times a, you distribute it into the 0 times a plus 0 times a. Alright? And then you subtract, or you apply the inverse of 0 times a. You subtract the 0 times a from left and right side. So you will get 0. This side is 0 times a. You see? You subtract the 1 copy. So here, right side, you still have a copy. This part, there's no copy, so you put the 0 here. So that's the steps to get 0 times whatever number is equal to 0. You see? If you have addition, identity of the addition times any other number, it's always this 0. Okay, so that's the proof. When we have this proof, we can apply this. See, 1 plus negative 1 is equal to 0. It's one proof. Okay. And then 0 times a is equal to 1 plus negative 1 times a. So it is equal to 1 times a is a, because 1 is the multiplication identity. It times everything is itself. And plus negative 1 times a. 0 times a, from the first step, we know it is equal to 0. So a number plus another number is equal to 0. So the other number is inverse. So negative 1 times a is the inverse of a. Inverse of a, we write negative. Okay, so that's a negative 1 times a is equal to negative. Okay, you see here, all the steps are based on the postulate, not based on our common sense. The common sense actually not that straightforward, because a common sense, you have so many common sense. You have to memorize many common sense. But postulate, you just start from those 8 postulates, you can get those this common sense. Okay. And when you have negative 1 times a equal to negative a, then you can also see that a plus this number is equal to 0. So a is the inverse of this. A is the inverse of negative 1 times a. Negative 1 times a is negative a, so it's a negative a. This is negative a, the inverse of it. Okay, so this is another property. A is equal to negative a, the inverse of the inverse of a. Okay. Actually, from here, you can see that the negative 1 times negative 1 is equal to 1. Why? Because negative 1 times negative 1 is negative of negative 1. Negative of negative 1 is the inverse of the inverse is a, is 1. So you see, the first property is just a special case of the second one. Correct? And for the third property, the negative of a minus b is equal to b minus a. How do we know that? If you want to find the inverse of a minus b as b minus a, you just add them. A minus b plus b minus a. You do addition, the sum is equal to 0. A negative a, the sum is 0. Negative b, b is 0. So it means this number is the inverse of the first one. The second number is the inverse of the first number, so the second number is written as the inverse of the first number. Correct? Okay, so here we're trying to practice the postulate. Okay, it's very important for you to understand how we get those steps. All the conclusions are very straightforward, but the reasons between steps are very, very different. They are not straightforward. And properly, the result for if you have AB in R and A times B equal to 0, then either A is 0 or B is 0. Okay, so how do we show this? We show this by the following. We assume A and B are both non-zero. Okay, if both A and B are non-zero, then what we have? We have A inverse and B inverse. For all the non-zero element, the inverse, multiplication inverse exists. Okay, so they have inverse. They have inverse. We multiply AB equal to 0 by A inverse. We get what? A inverse times AB is equal to A inverse times 0. A inverse times 0, we just notice that 0 times any number is 0, so it is equal to 0. And A inverse times A is equal to B. A inverse times A is identity. Identity times B is B. So we get B equal to 0. So that's a contradiction. We assume both are non-zero. That's wrong. So your assumption is not correct. So if A is not 0, you will definitely get B equal to 0. Actually, well, my proof is not very good. We actually only need to assume A is non-zero, right? Yeah, let me rewrite it. Assume that A is non-zero. Then A inverse exists. Then multiply AB equal to 0 by A inverse, we will get A inverse AB equal to A inverse times 0. It is equal to 0 here, then this B is equal to 0. So if A is non-zero, then B is 0. Assume that B is non-zero. Then B inverse exists. Alright, B inverse exists, then multiply AB equal to 0 by B inverse. Of course, this time it's from right hand side. We will get B inverse is equal to 0 times B inverse. It is equal to 0. So B times B inverse is identity. Identity times is 1. 1 times A is A. So A is equal to 0. So if A is not 0, B is 0. If B is not 0, A is 0. So either A is 0 or B is 0. Either or. Alright? So actually here I gave two proofs. This one is done by contradiction. If they are both non-zero, you will get a contradiction. It's different. I mean, it's not that good. Here we assume A is non-zero, B is 0. B is non-zero, A is 0. So either A or B is equal to 0. So all these steps are based on the properties in the postulate. Okay? Okay, the second postulate. For the numbers, we have two operations, addition, multiplication. We also have orders, which number is bigger, which number is smaller. So order postulate. Order axiom. Order axiom says there is a relation lesson on R cross R, the set of real numbers cross the set of real numbers, that has the following property. Okay, the following property. What are the following property? The first, trichotomy property. The property says given A, B in R, 1 and only one of the following statement holds. Either A less than B, or B less than A, or A is equal to B. So you have three cases. One and only one holds. So that's why it's called a trichotomy property. Okay. And second property, transitive property. Transitive property. Transitive property says if A is less than B and B is less than C, then A is less than C. It's transitive. 3, additive property. Additive property says if A is less than B and C belongs to a real number, then A plus C is less than B plus C. A plus C is less than B plus C. The addition does not change this relation. Property 4, multiplicative property. Multiplicative property. So A is less than B and C is greater than 0, then AC is less than BC. And A is less than B and C is less than 0, then BC is less than AC. So you multiply this inequality by a negative, multiply this relation by a positive number, you keep the relation. You multiply the relation by a negative number, you reverse the relation. Correct? So this is a complete postulate 2, the order axioms. Order axioms. All this is straightforward, the common sense for us, but here we just try to list them as a the basic, the ground stone for the common sense. Many properties will come from this postulate. Okay, so in this postulate, we only define the less than case. So here we have some remarks. If we write A greater than B, we mean A is less than B. B is greater than A, we mean A is less than B. Okay, and by A is less than or equal to B, we mean A is less than B or A is equal to B. By A less than B less than C, we mean A less than B and B less than C. Or it's just the common stuff. And for A in R, A is called non-negative. If A is greater than or equal to 0. A is called non-positive if A is less than or equal to 0. Non-negative greater than or equal to 0. Non-positive less than or equal to 0. Positive if A is strictly greater than 0. Negative if A is less than 0. Okay? And then, as we already mentioned, we have some categories of numbers. We can classify the numbers. We have the natural numbers. We have the the integers. We have the rational numbers, and we have the real numbers. The natural numbers, integers, rational numbers, and the real numbers. They satisfy the following conditions. So one is containing the other one as a proper subset. All right. Okay, so in the next remark, we just collect some basic information about integers and natural numbers. So we assume that natural numbers and integers satisfy the following properties. What are the following properties? 1, given n in Z, 1 and only one of the following statements holds. Okay, so for an integer, either it belongs to natural numbers, or its inverse belongs to the natural numbers, or it is 0. So it belongs to natural numbers, positive. Its inverse belongs to the natural numbers, it's negative. N is negative. N itself is negative with negative sign is positive, or N is 0. So that's obvious. Okay. And second, if n belongs to the natural numbers, then n plus 1 also belongs to the natural numbers, and n is greater than or equal to 1. So basically the smallest natural number is 1. So we can do addition always. And if n belongs to the natural numbers, then and n is not equal to 1, n is not 1, n is not the initial, then n minus 1 also belongs to the natural numbers. So we can do subtraction except 1. Okay? For if n is an integer and n positive, then n belongs to the natural numbers. Well, that's for sure. That's actually the first statement. That's the first statement. All right. So this remark is a groundstone for the so-called mathematical induction. Recall that mathematical induction always starts from n equal to 1 or maybe other initial value. And then every time you add the index by 1, you will exhaust all the required indices. Okay? So that depends on this remark. Every element you add 1 is still in this. Every element you subtract 1, if it's not 1, it is still in this. So basically you can think about it. All the integers can be exhausted by adding 1, adding 1, adding 1 many times. Okay? So, and another useful proof is the proof by contradiction. We actually already used. Proof by contradiction. Proof by contradiction means you have the conclusion. You assume the conclusion is incorrect. And then start from this assumption, you get deduction, and eventually you see some crazy result. Those crazy results contradicts to the known fact. Okay, if that happens, you will say okay, because at the beginning you assume something, but definitely that assumption is incorrect. Your assumption is incorrect. The original statement is true. Remember that your assumption is to assume your assumption is to assume the conclusion is incorrect. Okay, so your assumption is to assume the conclusion is incorrect. And then you prove that your assumption is incorrect. Okay, your assumption is incorrect, then it means your conclusion is correct. So that's a proof by contradiction. Okay, so we are going to do some examples to practice some of those strategies. Okay, let's see some examples about proofs. First, if A is in R, prove that A is not equal to 0 implies A squared is strictly greater than 0. And in particular, -1 is less than 0 is less than +1. Okay? Alright, let's see the proof. So here we assume A is not equal to 0. Then A is either greater than 0 or A is less than 0. Okay? Trichotomy property says 3 cases, one and only one case holds. So this one does not hold, so either the first hold or the second hold. Okay, so we have 2 cases. Case 1, A is greater than 0. A is greater than 0. A is greater than 0. So we are going to multiply this inequality by a positive number. Then A squared is greater than 0 times A. 0 times A we proved it is 0. So A squared is greater than 0. Correct? Sure. And second case. A is less than 0. A is less than 0. A is less than 0. When you multiply this inequality by a negative number, you're going to change the direction of inequality. Here is less than, now it becomes greater. And 0 times A again is 0, so A squared is greater than 0. So either case, you will have this. All right, and for the proof, -1 is less than 0, less than 1 is easier. 1 is not equal to 0, and 1 squared is equal to 1, of course, is greater than 1. Right? Correct? Okay, and then what we can do, we can have the following thing. We are going to subtract 1 from 2 sides. One minus 1 is 0. You see? Let me write this step complete. 1 minus 1 is greater than 0 minus 1. 1 minus 1 is 0. 0 minus 1 is -1. 0 minus 1 is -1. So it's a 0 greater than -1. So 1 greater than 0, 0 greater than -1. So -1 less than 0, less than 1. Okay, so at this moment, whenever you try to prove some obvious result, try to see if you can find the rhythm behind the steps. Don't use your common sense. Use the postulate and use the property axioms you just learned. All the conclusions are simple, but we just try to practice the reason. All right. Let's see another example. So if A is in R, prove that A between 0 and 1 implies 0 less than A squared less than A, and A is greater than 1 imply A squared is greater than A. Okay, so it has 2 parts. First one, 0 less than A less than 1. Because A is greater than 0, it's a positive number. We are going to multiply this inequality by a positive number. 0 times A less than A times A less than 1 times A. 0 times A is 0. A times A is A squared. 1 times A is A. So we directly have it. Right? And a greater than 1. We know 1 greater than 0, so a is greater than 0. We multiply this inequality by a positive number, so we get a times a greater than 1 times a, so a squared is greater than a. That's the second part. Correct? Yeah. So similarly, you can try the following thing. Try to prove that the conclusion 7, if 0 is less than or equal to a less than b, and 0 is less than or equal to c less than d, imply AC less than BD. Try to show this. 8. 0 less than or equal to A less than B implies 0 less than or equal to A squared less than B squared. And 0 less than or equal to square root of A less than square root of B. 9. If we have two positive numbers, 0 less than A less than B implies 1 over A is greater than 1 over B is greater than 0. Be careful, all these results are trivial. Just make sure you can go from one step to the next step based on the postulate. All the result we just proved. Don't jump between steps. All right? Okay, so my cell phone can only take a video about 55 minutes. So I'm going to stop this video at this place, and we will continue the discussion in the next video. Okay, so try to practice those proofs. They are not difficult, but you need to clearly clearly understand what is the rhythm between the lines. Okay, so I finish this video and start in a new video.